In this video, we solve a problem from written homework number 4 from the spring 2021 semester in the elementary differential equations class at Tulsa Community College, excuse me. We have a fourth order homogeneous linear ordinary differential equation with constant coefficients. And we need to find the general solution to that and then use the 4 initial conditions to find the 4 values of the constants. Since it's a fourth order equation, we know the general solution has the form C1y1 plus C2y2 plus C3y3 plus C4y4. Those constants, C1, C2, C3, and C4 can be found using these initial conditions. So that's the plan. Once we find those constants, we'll substitute them in, and that will give us a particular solution to the IVP. But first, we need to find the general solution of the differential equation. Since we have a constant coefficient homogeneous linear ordinary differential equation, we're going to let y equal e to the mx, and then we'll compute the derivatives as necessary. So we're going to need y prime, y double prime, y triple prime, and the fourth derivative of y. Every time we take the derivative of e to the mx, if I had e to the 3x, I'd get e to the 3x times the derivative of the inside, which would be a 3. In this case, m is the constant. So we're going to have m times e to the mx there. The second derivative is going to be m times the derivative of e to the mx. So we'll get another m when we take the derivative again. And when we take the derivative again, we'll get another m. All of those extra m's come from the chain rule. Now we're assuming that y, this is a fourth order equation, so I need the fourth derivative. Multiply by m again. We're assuming that y is a solution to this differential equation. So we want to replace the fourth derivative, third derivative, second derivative, first derivative, and y itself with all of these functions. If y equals e to the mx is a solution of that equation, then these functions will satisfy that equation, so we can plug them in. Let's do that. We'll substitute into the differential equation now. We have the fourth derivative of y minus 6 times the third derivative of y plus 9 times the second derivative of y, which has an m squared in it, plus 6 times the first derivative of y, which has an m in it. And then we have minus 10 times y. We were assuming that y was equal to e to the mx. We set that result equal to 0. Okay. Now you factor out the e to the mx from here, and you're left with this e to the mx times this fourth degree polynomial equation, or times the fourth degree polynomial, excuse me, and that has to equal 0. Well, exponential functions are always positive, they're non-zero. So that means that the polynomial must be 0. Now, if you know how this factors, you can just go ahead and factor it. But it's not obvious to me how this factors. One thing I noticed, though, is that if I just add the coefficients, like this is a 1 plus a 9 is 10. 10 minus 10 is 0. I've got a negative 6 there and a 6 there. Negative 6 plus 6 is 0. If I add the coefficients, I get 0. So that tells me that m equals 1 is actually a solution to this. Now, typically, I would go to possible rational roots at this point, but I already know that m equals 1 is a 0 because I just sort of replaced m with 1, and I said 1 minus 6 plus 9 plus 6 minus 10 is going to give me 0. I did that in my head, but let's write it down and show that we get it if we do the arithmetic. This is 1 minus 6 plus 9 plus 6 minus 10. The 6 and the negative 6 undo each other. Those reduce. And then we've got 10 minus 10. Those reduce. So that equals 0. So that means that m equals 1 is a 0 of the polynomial, or you can say that m equals 1 is the root of the polynomial. Um, and that means that m minus 1 is a factor. So if you didn't know how to factor this, you could list the possible rational roots, then try different values of m on that list until you got one that actually gave you a root. But I got to skip that step because I noticed right away that m equals 1 was going to work. So now I want to divide out m minus 1 from this guy. This is a 4th degree polynomial. So it's going to be factored as a linear polynomial, m minus 1 times some quotient, and that quotient will have a degree that's 1 less than the 4th. So if this is 4th degree and we divide out something that's linear, this is going to be a 3rd degree polynomial. To figure out what 3rd degree polynomial that is, we're going to do synthetic division. So in this case, I just showed that m equals 1 is a root, which meant that m minus 1 is a factor. And now we want to factor that out or divide that out. We're going to find Q using synthetic division. Okay, now the way synthetic division works is you put the value of the root in the box over here. So if you're dividing this by m minus 1, you put, well, whatever you get when you set this equal to 0 and solve for m in the box. It's the same as the 0 that corresponds to that. So m equals 1 goes there. And then you list the coefficients of this 4th degree polynomial. So there's an implied 1 there. And we've got an m to the 4th, m cubed, m squared, m to the 1st, and a constant term. So we've got all the powers of m in descending order. That's what we want. Just list the coefficients. If I'm taking this and I'm dividing it by m minus 1, the quotient will be what we get. We'll be able to find that quotient q of m by using synthetic division. So with synthetic division, you list the root here, you list the coefficients of your polynomial that you're dividing in descending powers of m. Bring the first number down, multiply and add, multiply and add, multiply and add, multiply and add, and that's good. Whatever's over here should be the remainder. The remainder should be 0. If the remainder is 0, then you know that m equals whatever that value is a 0, and m minus that value is a factor. And we knew that that was going to work because we plugged in m equals 1 and we already got 0. So if we get something other than 0 right here, that means it's not going to work. That means that value of m is not a 0 of the polynomial. But this time it worked the way it's supposed to. So this is telling us that q of m has these coefficients. It was a 4th degree polynomial. We divided out a 1st degree polynomial. So q is going to be a 3rd degree polynomial. So the original polynomial can be written as m minus 1 times q, where q has these coefficients. So this is a coefficient of m cubed because it's cubic. So we're going to have 1m cubed minus 5m squared plus 4m plus 10. And now we're here. And then we say to ourselves, okay, can I factor that easily? And it doesn't look like it factors easily. I can't just factor by grouping. So this time I am going to use possible rational roots. Just focused on this piece and not too worried about that. I'm just going to bring that m minus 1 factor down. Let's see, if m equals 1, again, will it work? If m equals 1, I'll have 1 plus 4, that's 5. 5 minus 5 is 0, plus 10 is 10, not 0. So m equals 1 won't work. Let's list the possible roots of possible rational roots of this cubic polynomial. So we take the factors of the constant term. In this case, that's 10. And we divide by the factors of the leading coefficient. There's an implied 1 there. So factors of 10 are plus and minus 1 and plus and minus 10. plus and minus 2, and plus and minus 5. And of course, dividing by plus and minus 1 doesn't really do anything. So we've got 8 possible rational roots, 1, 2, 5, and 10, and -1, -2, -5, and -10. Now, I already checked m equals 1 in my head. 1 plus 4 is 5, 5 minus 5 is 0, 0 plus 10 is obviously not 0. So m equals 1 does not work. Not this time, not for this guy. But I think -1 might work. So I want to try this one. And my thought with the -1 was, well, if I plug in -1, that would change these signs. So I'd have a -1, a -4, and a -5, and that would give me -10 plus 10, which would be 0. So I'm thinking through that in my head, and then I will verify that by doing the arithmetic down here. And so I've got -1, -1 squared is +1. And what do you know? We get -10 plus 10, which is 0. So m equals -1 is a root or a 0 of the polynomial. And if that's true, then m minus a -1, that's m plus 1, is a factor of that polynomial. And I'm going to call that polynomial q for right now, or I'll call it q1. Was our first quotient. Okay, so this guy is m plus 1 times a different quotient. This is cubic. So if I divide that cubic polynomial by a linear polynomial, or I'm dividing a 3rd degree polynomial by a 1st degree polynomial, the power goes down by 1. So this is going to be a quadratic polynomial. It's going to have an m squared term in it. To find that quadratic polynomial, and I'll call that one q2 just to have a label for it, we take the value of m that corresponds to this factor. That's the root corresponding to that factor of -1. You put that in the box. Then you list the coefficients of this polynomial right here. So we've got a 1, a -5, a 4, and a 10. We do our synthetic division again. Bring down the 1, multiply, and add. Multiply, and add. Multiply, and add. All right. So these are the coefficients of the quadratic polynomial that's left. So we've got m minus 1 from before, then we had the m plus 1, and then the quadratic that's left over has coefficients of 1. So we have a 1m squared minus 6m plus 10, and that equals 0. Now, if this factored, we would factor it, but I can't think of two numbers that multiply to give me 10 that add to -6. So I'm going to complete the square on that. This is as factored as much as possible without using complex roots. So let's find the zeros, or the roots of that polynomial. Find m1, m2, m3, and m4. So from this one, we have m minus 1 equals 0. So if you add 1 to both sides, you get m equals 1. So m1 equals 1. Over here, you set that equal to 0. Subtract 1 from both sides, you get m2 equals -1. Over here, I'm going to complete the square again. So I subtract 10 from both sides. I identify b, take half of that, and I square it. -3 times -3 is +9. So we add 9 here and add 9 there. And then we complete the square. Or that's how we complete the square. This is a perfect square. It's m minus 3 times m minus 3, or in other words, m minus 3 squared. And you simplify on the right-hand side, -10 plus 9 is -1. Okay. if this is what you get if you say, I'm looking for two numbers that multiply to give me positive 9 that add to negative 6. Okay, now I want to get m by itself, so I take the square root of both sides. Don't forget the plus or minus on the right. Square root of negative 1 is called I. Then we'll add 3 to both sides. This is m1, that's m2, so we'll call these m3 and m4. This is alpha plus or minus beta times I. Alpha must be 3 then, and beta is the number in front of the I, that positive number, so beta is positive 1. Okay, so after we have factored our characteristic equation, we solved for m1, m2, and m3, and m4. We need 4 of them because it was a 4th degree polynomial. It's a 4th order differential equation. Once you have those, you can use those to find y1, y2, y3, and y4. Those 4 linearly independent solutions. Well, y1 comes from e to the m1x because this is a distinct real root. m1 is 1, so this is e to the x. Y2 is e to the m2x. m2 is negative 1, so it's e to the negative x. Here we have complex conjugate roots, so we're going to have a sine-cosine pair. E to the alpha x times cosine of beta x. Alpha is 3. Beta is 1, so it's just cosine of x. And y4 looks just like y3, you just change the cosine to a sine. And then the general solution, since it was a 4th order equation, is c1y1 plus c2y2 plus c3y3 plus c4y4. So that's c1 e to the x plus c2 e to the negative x plus c3 e to the 3x cosine of x plus c4 e to the 3x sine of x. That's true. That works on negative infinity to infinity. Okay, now if we were asked for the general solution, we would be done. That is the solution to this differential equation. But we've got an initial value problem. So that means, since it was a 4th order equation, there's a lot of derivatives to compute here. We need y prime, y double prime, and y triple prime. And once we have y double prime, or y prime, y double prime, and y triple prime, we can use these 4 initial conditions to find 4 equations and 4 unknowns. And then we'll solve that system of 4 equations and 4 unknowns for C1, C2, C3, and C4. Okay, so we've got y here. We need y prime, y double prime, and y triple prime for our initial conditions. Y prime, let's do that. Okay. So we have the derivative of a constant times e to the x is the constant times e to the x. The derivative of a constant times e to the negative x is that constant times e to the negative x times the derivative of the inside, which is a negative 1 by the chain rule. Here, we need to use the product rule. And we have to use the product rule for that expression as well. So according to the product rule, this is what we get. We've got the derivative of the first. And we get e to the 3x times the extra 3 derivative of the inside by the chain rule. It's derivative of the first times the second, plus the derivative of the second. Derivative of cosine is negative sine of x, times the first. Okay, so that's a product rule for this one. Now, for this one, same thing. Derivative of the first. Bring the constant down. Derivative of e to the 3x is e to the 3x times an extra 3 by the chain rule. Derivative of the first times the second. Plus derivative of the second. Derivative of sine is cosine times the first. Okay, so that's y prime. Now, if you want to, You can simplify it. I would simplify it by grouping the cosines together and the sines together. So I've got these two guys. So that's 3c3 plus c4 times the exponential times cosine of x. And then with the sines, I want to group those as well. So I'll have negative 3c3 plus 3c4 times the exponential times the sine function. Okay, so that's my y prime. Now I need to compute y double prime. Derivative of a constant times e to the x is that constant times e to the x. Then you bring the negative c2 down. The derivative of e to the negative x is e to the negative x times the derivative of the inside. And -1 times that is going to give me that. Then over here, I want to use the product rule again. Derivative of the first is this constant times the derivative of e to the 3x. So that's going to be e to the 3x times this constant times 3. If I distribute that 3 to everything, I'll have 9c3 plus 3c4. So that's the derivative of the first times the second, plus the derivative of the second, which is -1 times sine of x, times the first. So that's all of that. Okay. Similarly, this is my first function and this is my second function. I want derivative of the first. The derivative of a constant times e to the 3x is that constant times e to the 3x. The derivative, or times the derivative of the inside, which is a 3. So 3 times this constant is going to give me a -3c3 plus 9c4. That's the derivative of the first. We're multiplying it by the second function, which is sine of x. And then we're adding the derivative of the second times the first. Derivative of sine is cosine. So we'll just have this. You leave that first function alone and you multiply by cosine. Now we want to collect like terms involving x, or cosine of, or e to the 3x times cosine of x and e to the 3x times sine of x. So I'm going to group these two guys together and I'm going to group these two guys together on the next page. This one takes some time. It's a good exercise. Okay, so let's group the cosine terms first. I've got e to the 3x cosine of x and e to the 3x cosine of x here. So I've got 9c3 plus 3c4 minus c3 plus 3c4. So 9c3 minus c3 is going to give me an 8c3. And 3c4 plus 3c4 is 6c4. Okay, so those guys are gone. Now over here, with the sine functions, e to the 3x times sine of x and e to the 3x times sine of x, we want to group as well, but we have to distribute that negative. So we're going to have, oops, there's something missing here. It should be a c4, not a 4. So we'll have -3c3. Actually, that should be a 3 as well. I'm sorry. It's the derivative of, or that's, or excuse me. This is supposed to come from here. It's the derivative of the first. No, actually, no, this is the derivative of the second over here. This is supposed to be this, the first times the derivative of the second. So there's my first function, and the derivative of cosine is the negative sine of x. Okay, just making sure. Sorry about that, a little aside. I'm trying to group like terms for this exponential times sine here and here. You've got to distribute the negative. I have -3c3 minus 3c3 is -6c3. -c4 plus 9c4 is 8c4 times the exponential times sine of x. Okay, that's a lot. That's our y double prime. And it was a fourth order equation. So we need y triple prime as well. So we need to do this one more time. Derivative of a constant times e to the x is the constant times e to the x. Derivative of a constant times e to the negative x is that constant times e to the negative x times the derivative of the inside, which is a -1. So we're just subtracting that term instead. And then here, product rule again, there's my first function, there's my second function. We have derivative of the first. Derivative of a constant times e to the 3x is that constant times e to the 3x times 3. So I'm going to take this and multiply it by 3. 3 times 8 is 24. So it's the derivative of the first, and we're multiplying by the second. Then we're adding the derivative of the second, which is negative sine of x times the first. So my first function is here, sine of x is here, and I'm going to take each of these guys and multiply by -1. So it's going to give me a -8c3 minus 6c4. 6, not 8. Okay, so that was the product rule for that guy. Now we've got to use the product rule for this guy. Here's my first function, and there's my second function. So we're going to have this. Derivative of the first times the second. Actually, and the second function is sine of x, so I'm going to stack that vertically like this, put it right here. Derivative of constant times e to some power is that constant times e to that power times the derivative of the inside, which is a 3. So we're going to take this guy and we're going to multiply it by 3. So that's going to give me a -18c3 minus 24c4. That's derivative of the first times the second. Then we're going to add derivative of the second, which is cosine of x, times the first. Ooh, that's a lot. And so we get c1 e to the x minus c2 e to the negative x. And this is actually kind of nice because I stacked it vertically. It's easy to do the arithmetic. We've got 18c3 plus 26c4 times this exponential times cosine. And then over here, we have a negative 26c3 minus 30c4 times the exponential times sine. Okay. All right. So we have y prime, we have y prime, y double prime, and y triple prime. Now that we have all of those, we can use those to come up with 4 equations and 4 unknowns, C1, C2, and C3, and C4, using these initial conditions. So we're going to replace x with 0 and y with 3. We'll replace x with 0 and y prime with 4. We'll replace x with 0 and y double prime with 11, and so on. And that's going to allow us to find our constants. So let's go to the first one first. We have y of 0 equals 3. So that means that when x equals 0, y equals 3. Those are equivalent to each other. Usually I write it in the other order, but I wrote it in the wrong order this time. So I'm replacing x with 0 in my function y. And where is my function y? My function y was right here. So I've got c1 times e to the x plus c2 times e to the negative x plus c3 times e to the 3x times cosine of x plus c4 times e to the 3 times x times sine of x. And I'm replacing all of the x's with 0. Okay, sine of 0 is 0, so this guy is gone. E to the 0 is 1, cosine of 0 is 1. So we end up with y of 0 equals c1 times 1 plus c2 times 1 plus c3 times 1 plus c4 times 0, which is 0. That has to be equal to 3. We're looking for 4 equations with 4 unknowns. That is our first equation. All right, next one. We were told that y prime of 0 is equal to, let's see, where's the original problem statement? Y prime of 0 is equal to 4. So that means that when x is equal to 0, y prime is equal to 4. So let's find y prime. Y prime is right here. We're just replacing all the x's with zeros. So we're going to have c1 e to the 0 minus c2 e to the opposite of 0 plus 3c3 plus c4 times e to the 3 times 0 times cosine of 0 plus negative c3 plus 3c4 times e to the 3 times 0 times sine of 0. I have to be very careful with these things. If we write the wrong thing down, make a little transcription error, we'll make our answer very wrong. And that's okay because we're not so concerned about getting exactly the right answer. Our concern in this class is mostly that you understand the process and you understand how to solve differential equations. But if we want to be accurate, if we want to get the right answer, we've got to be very, very careful about whatever it is that we write down. So if we evaluate this y prime at 0, we get c1 times 1 minus c2 times 1. And then this is 3c3 plus c4 times 1. And then we've got something times 0, which is, of course, 0. We're going to set that equal to whatever they told us that y prime of 0 was. That was 4. That's our second equation. So I've got 2 equations with 4 unknowns so far. And to get the other 2 equations, we need to use the other 2 initial conditions. We've got y double prime at 0. They told us that y double prime at 0 was 11, which just means that when x equals 0, y double prime is 11. So it's a little tedious. That's okay. We're learning, getting this process down, making sure that we understand it. Sometimes it's worth the extra effort and the extra time because of the understanding that we gain. I love that personally, but I guess that's why I'm a math teacher. So we replace all the x's with zeros. And of course, sine of 0 is 0. This is a 1 and this is a 1. So we end up with an e to the 0 is 1. So we end up with c1 plus c2 plus 8c3 plus 6c4 times 1, which is just 1. And then we have this times 1 times 0. So that whole piece is gone. That is our y double prime at 0. We're setting that equal to whatever they told us y double prime was at 0. It was 11, not 0. Put the wrong thing down there. That is our third equation. We're looking for 4 equations with 4 unknowns. Almost there. Y triple prime at 0 equals 9 is the last initial condition. So that says that when x is equal to 0, y triple prime is equal to 9. Okay, so we go to y triple prime and we plug in 0. Okay, because sine of 0 is 0, this factor is gone. we're gonna end up with C1 minus C2 plus this expression. And we're setting that equal to 9 and solving from there. So finally got our 4 equations with 4 unknowns, and we're going to solve that system of 4 equations and 4 unknowns for C1, C2, C3, and C4. Okay, let's get this one. So it will be easier if I just start on a new sheet, and that's okay because I'll just use the back of that sheet for another problem. C1 plus C2 plus C3 has to be 3. And C1 minus C2 plus 3C3 plus C4 equals 4. C1 plus C2 plus 8C3 plus 6C4 equals 11. And C1 minus C2 plus 18C3 plus 26C4 equals 9. Okay, you got 4 equations and 4 unknowns. The whole idea here is this. We want to eliminate one variable at a time. So you're trying to get from 4 equations with 4 unknowns down to 3 equations and 3 unknowns. And the way we typically do that is by multiplying equations by constants and adding them together until we're left with 3 equations and 3 unknowns. And actually, I think that that's a really good approach here. We don't actually have to multiply too many of them by constants because of this, this flipping of the sign for C2 here when we took the derivatives. If I call this one equation 1 and this one equation 2, if I add these together, I'll get rid of the C2s. And if I call this equation 3 and this equation 4, if I add these together, I'll get rid of the C2s as well. So that will give us 2 equations with 4 unknowns. Or actually 2 equations with 3 unknowns, and we'll need a 3rd equation. But basically, you're going to choose. You're going to say to yourself, which variable do you want to get rid of? I'm going to choose to eliminate C2 because it looks the easiest to me. And the way I'm going to do that is initially I'll add these 2 equations together. And see what I get. So now I've got 2C1, those reduce, plus 4C3 plus C4 equals 7. So that's one equation with our 3 unknowns, C1, C3, and C4 now. So I'm going to call this my new equation 1 star. All right. So that's one way to get rid of C2. Another way to get rid of C2 is to take equation 3 and equation 4 and add those together. So we've got this. The C2s reduce, and we end up with 2C1 plus 26C3 plus 32C4 equals 20. Could just leave it like that. I notice all of these numbers are multiples of 2, so I will divide by 2. And we have C1 plus 13C3 plus, is that 16? C4 equals 10. This is my new equation 2. Now, I need to eliminate C2 one more time using different equations. I've already used these 2 together, and I've already used these 2 together. So now I just need to pick one from these 2 and one from these 2 and then add them together. So I think I'll do equation 2 plus equation 3. because those still have opposite signs. Equation 2 is right here. Equation 3 is here. Okay, got 2C1, those reduce, 11C3, 7C4, and then 15. All right. So we have to be systematic about this. You have to decide which variable you want to eliminate, and then you're going to use pairs of equations to eliminate that variable. But you have to use like 3 different pairs in order to go from 4 equations and 4 unknowns down to 3 equations and 3 unknowns. So this is our new system. Maybe I should have left that doubled. That's okay. Hindsight's 2020. Okay, and now we are trying to pick a different variable to get rid of. I think the obvious choice for a variable to get rid of is C1. I think we can take the second equation here. I call these equations 1, 2, and 3. 1 star, 2 star, and 3 star. I will take the second equation, multiply by -2, and I will add that to this equation, and I'll add that to that equation. And that will eliminate C1. So again, we're making a choice. And we're going to eliminate one variable at a time. So I'll take equation 1 star and take the second equation, multiply it by -2, and add them together. -2 times that is going to give me this. Okay. And then equation 1 star was this. And then when we do that, we get this. It's not the prettiest equation I've ever seen, but it's okay. We got rid of the C's, or C1s, and now we have one equation involving C3 and C4. Now we want a second equation involving C3 and C4. I'll call this 1 double star. So last time we used equations 1 and 2. Now we have to use equations 3 and 1 of these. Either one would be fine. Actually, since these are almost identical, but equations 1 and equation 3, they both have the 2C1. I think I'll use those this time. And since these numbers are bigger than those numbers, I think I'll take equation 3 star and subtract equation 1 star. So we're subtracting equation 1, which just means we're changing all the signs. All right. So you see how we do that? We choose a variable to eliminate, and then we take 2 equations and eliminate it, 2 equations and eliminate it, and 2 equations and eliminate it. They have to be 3 different pairs to get from 4 equations and 4 unknowns down to 3 equations and 3 unknowns. Then similarly, we're trying to get from 3 equations and 3 unknowns down to 2 equations and 2 unknowns. So we pick a variable we're trying to get rid of. We're trying to get rid of the C1. Then we get rid of it by choosing 2 equations. I use these 2, and then 2 different equations. So 2 different equations in this case required us to use equation 3. And now you've got 2 equations and 2 unknowns. Those are right there. Now we want to solve this system of two equations and two unknowns, or we want to solve that system of two equations and two unknowns by writing it as one equation and one unknown. So we want to eliminate either C3 or C4, whichever one we want is fine. So this is a little tedious, but hopefully by going through this process, you get it. That's the idea. You're like, oh, okay, I'm just picking a variable to get rid of, and then I get rid of it by picking pairs of equations. That's exactly how we do that. Okay, now when I'm looking at the 31 and the 6, or the 22 and the 7, like which one is going to be easier? I think I'd rather work with the 22 and the 7 personally. It really doesn't matter. Let's eliminate C3. If you eliminate C4, that's okay. The methods are still going to give you the right answer, the same answer eventually. Now, if I want to get rid of C3, I'll multiply this second equation by 22. And I'll multiply the first equation by 7. And I'll add those together. So I have negative 154 times C3, and 7 times 31 is 217, and 7 times 13 is negative 91. If I take this guy and I multiply by 22, I get positive 154 times C3, good, and 22 times 6 is 132 times C4, and I have a 176 over here. Then those reduce, and we end up with this negative 217 plus 132. It's negative 85 times C4 equals 176 minus 91. Hey, that's nice. That's a good sign. So it looks like C4 must be negative 1. Nice. And now that we know that C4 is negative 1, we can use any one of these equations to find C3. So that is that process. You go from 4 equations and 4 unknowns down to 3 equations and 3 unknowns by choosing a variable to eliminate. Then you go from 3 equations and 3 unknowns down to 2 equations and 2 unknowns by choosing a variable to eliminate. Then you go from 2 equations and 2 unknowns down to 1 equation and 1 unknown, and then you solve it. And then you go backwards, you back substitute. So I have C4 equals negative 1. I can substitute C4 equals negative 1 into this one or this one and solve for C3. I will use equation 2 double star to solve for C3 now. Okay, so we've got 7C3 plus 6 times C4 equals 8. So 7C3 minus 6 equals 8. Add 6 to both sides and divide by 7. And we get C3 equals 2. That's very nice. You can tell it's a textbook problem. So I've got C3 and C4 now. And then we just keep going. We go back. Now we want to go back to our 3 equations and 3 unknowns. So we go back here. We know what C3 and C4 are. We want to find C1. So we can substitute C3 and C4 into, let's just say, equation 1 star. So if C4 equals negative 1 and C3 equals 2 into equation 1 star to solve for C1. Okay, so we have 2C1 plus 4 times C3 plus C4 equals 7. And C4 was -1 and C3 was 2. So we've got 2C1 plus 8 minus 1 equals 7. So we've got 7s on both sides. So subtract 7 from both sides and you get that. So C1 must be equal to 0. Divide both sides by 2 and you get 0. Okay, so now we have C1, C2, or C1, C3, and C4. We need C2. Go back to your original 4 equations and 4 unknowns. If I know C1 and C3, I can find C2 from right there. So let's substitute C1 and C3 into equation 1 to find C2. So we've got this. C1 plus C2, which is unknown, plus C3 equals 3. And C1 was 0 and C3 was 2. So C2 plus 2 equals 3. So C2 equals 1. Awesome. So now we know that C1, C2, C3, and C4 have those values. Now if we want the particular solution, we have y equals C1, Y1 plus C2, Y2 plus C3, Y3. It's been a while. Where is that sheet? I think it was this one. Yeah, this was our original solution. So we just have to replace C1, C2, C3, and C4 with the values that we found. So y equals C1 times e to the x. Well, C1 was 0, so there is actually no e to the x term. Plus C2 times e to the negative x. So we have 1 times e to the negative x. Plus C3, which is 2, times e to the 3x times cosine of x, plus C4, which was -1, times e to the 3x times sine of x. That's going to work on negative infinity to infinity. That is how we solve the initial value problem. Oh, that was a good example because it really shows you how to solve systems of equations. It's a little tedious and it's very easy to make some little arithmetic mistake somewhere. But hopefully by going through that process, you see the rhythm to it, the pattern of just choosing a variable to eliminate and eliminating it, and choosing a variable to eliminate and eliminating it. And you just reduce one variable at a time until you find the value of one of them. And then you use that one and back substitute to find another one. And then you use those two and back substitute to find the other one. And then you use those 3 and back substitute to find the last one. So I think this is a beautiful example of that process. And the systems of equations happen to be really nice because it's a textbook problem where C1, C2, C3, and C4 were nice small integers.